you everybody for coming today. My name is Josh Lewis. I'm here to talk about mechanical systems today and tomorrow for this Better Buildings Bootcamp 2021. So just a little bit about me before I get into it. I'm the engineering manager at the Nerva Energy Group. We are a specialty contractor who provides energy advisory services as well as smart building optimization. I have a couple of awards to my name that you can see there. And in terms of my involvement with this topic and Sustainable Buildings Canada, I am a subject matter expert for mechanical and building automation systems for the Enbridge Savings by Design program, which of course is put on by SBC. I am speaking at the Green Building Festival coming up in October. Hope you can join me there. And I also am the founding president of the Association of Energy Engineers Southwestern Ontario chapter. So, when we look at mechanical systems and really when we look at buildings in general, what is the market trying to do? What are the owners, what are the developers trying to do? Certainly, they're not all the same, but generally they're trying to maximize their cap rate, which is their net operating income versus the current market value of the asset. Of course, part of that is decreasing build costs and decreasing operational costs of our buildings. But we also have to be thinking about the future too as well. Improving tenant comfort and health, increasing the resiliency of buildings. So the resiliency of buildings here is defined as the ability for the building to respond to adverse events such as, extreme weather, power outages, utility outages. But we also have to protect for utility cost increases as well. And, to that point, I don't think the market generally realizes. Actually, you know what? I won't say think. I know that the market generally does not realize what is going to be happening to the cost specifically of natural gas over the next 10 years and beyond that due to the carbon tax. Essentially right now, because the carbon tax is going from $30 a ton to $170 a ton by 2030 and expected to increase after that, our real cost of natural gas in Ontario is increasing at a rate of 13% year over year. I mean, that is a very high year over year increase. That's way above any kind of inflation. So essentially by 2030, we're looking at natural gas costs in Ontario of 2 to 2.5 times more expensive and continuing to increase. And all of this is not dependent on whether the commodity increases. If the commodity also goes up, then that could be, 3 times more expensive or even more. So, gas-fired equipment has a minimum 20-year lifespan typically. So decisions we're making today to buy, install, commission gas-fired equipment actually has huge impacts over its life cycle. This is new. This is just, it's not new in the sense of the carbon tax, but it's new in terms of the realization that people are coming to in the market now that the decisions they're making today are going to have this huge operational cost impact, never mind obviously the carbon emissions as well in the future. Now, just for comparison's sake, electricity is forecasted to increase between 3 to 6% annually, so much less than gas. Electricity in Ontario is fairly carbon clean, so it's not driven by the carbon tax as much, but the electricity costs are political typically because they end at the borders of political borders. So that 3 to 6% increase might be conservative. It might be more than that, but unfortunately there's political factors there that we can't predict. So now that we talked about utility costs, mechanical systems. So, an energy efficient and comfortable building always starts, first of all, with a high performance building envelope, then well-designed mechanical and electrical systems. But I think we can all realize ultimately that if a building cannot be built, operated, and maintained successfully, it's never going to achieve those goals you're trying to go for it, right? The comfort, the efficiency, the health, the wellness, it's never going to get there. So what we're going to talk about in this session is like an integrated approach, but we're first going to talk about, okay, what are the mechanical systems we're talking about? What are those kind of key design criteria, and how do you look at designing those systems for a building or picking those systems? What is the history and current state of typical mechanical systems within buildings? as well as what do we need to consider due to the COVID-19 pandemic. That's actually an extra set of slides at the end, specific to some of the things that have come out of the COVID-19 pandemic and what we've had to do to buildings to make them safer. So let's start with some definitions, right? So for today, mechanical systems are those required to maintain the desired environmental conditions within a space, within a building, right? So primarily HVAC, the temperature, the humidity, the CO2 levels, the particulate, the volatile organic compounds, and also pressurizing the building as well. That is where most buildings spend the majority of their mechanical system energy. It's in that, and the majority of their energy overall is in the HVAC. Now, we also have hot and cold water. I'll obviously touch on that a little bit today as well. Lighting, I'm not going to talk about too much because lighting these days is fairly prescriptive. Really, it boils down to LEDs, which everybody is using these days, both for retrofit new designs, having a well-designed lighting so you're not overlighting the space, as well as having controls for lighting, which are typically occupancy sensors or master off switches, which are becoming more popular in multi-res, where you have one switch near your door and you can shut off all the lights in your unit when you leave, or when you come back on, you can turn them on with one switch. There's not really much else to say in terms of lighting. There's little sub-optimization strategies, but overall, we're in a pretty good place compared to where we used to be back in the fluorescent or even incandescent days. Some other mechanical systems that are typically in larger buildings, but we're not going to touch on today because they're kind of unique, are things like elevators, pools, and garbage compactors. Certainly, there's strategies for efficiency within elevators and pools, but those are more detailed subjects. Now, that term though, HVAC/R, actually, if you want to add it all on there, what does that actually mean? So when someone says that acronym is heating, ventilation, air conditioning, and the /R is refrigeration. Now, when we're talking about refrigeration, which what refrigeration is referring to there is not your fridge, is not your freezer in your house. That's like the refrigeration systems on grocery stores, warehouses, hospitals, large restaurants, cafeterias, those types of refrigeration systems, which are certainly out of the scope of what we're going to talk about today, but something to consider if they are a major energy use. For example, a typical grocery store uses somewhere between 30 to 50% of their total energy usage just on the refrigeration cases, both the fridge cases and the freezer cases. But that's outside the scope of today. One other note, this is my building automation side of me talking, is that you do need to consider from the earliest stages a high level of coordination between the mechanical systems and the building automation system or the building management system, whatever acronym you're using, because the best controls can not optimize a system which is inherently uncontrollable. So looking at mechanical and building automation in separate buckets isn't really the right way to do that. We want to build those two things together from a design perspective in order to get the best results and in order to ensure that they're integrated properly from the earliest points of the design. Now, where did this all start? Well, it started with ASHRAE, the American Society of Heating, Refrigeration, and Air Conditioning Engineers. So this is a very old professional society in terms of societies that were born out of the Industrial Revolution. They were founded in 1895. They currently have about 57,000 members in more than 132 countries in the world. And ASHRAE funds research projects, continuing education programs, but primarily what they're known for is they develop and publish technical standards. So when it comes to the fundamental standards for mechanical systems for buildings, ASHRAE sets the standard in terms of building services engineering, energy efficiency, indoor air quality, sustainable development. Now, ASHRAE standards are the base. A lot of localities, a lot of countries, a lot of municipalities, provinces, states may take the ASHRAE standards and then do amendments to them, but the ASHRAE standards are still the base. And some of the most known or well-recognized standards is starting with ASHRAE 90.1. Probably the most well-known standard, and that's the energy standard for buildings except low-rise residential. There's also 62.1, very close behind, ventilation for acceptable indoor air quality. 55 is thermal environmental conditions for human occupancy within buildings, and 189.1 is the standard for design of high-performance green buildings, except, again, low-rise residential. ASHRAE has way more standards than these. And these standards are very technical. They're very data-driven. They're very math-based, table-based, standards-based. they're really the go-to guides for engineers to use to design buildings. They're what building code departments use to set standards for their buildings. And so this is really where it all comes from, where it started, and who's kind of this master gatekeeper of all of these different components within buildings, which obviously directly affect the mechanical systems. Now, when we're talking about designing mechanical systems for buildings, I've got 9 key design criteria. This is the way that I look at it. Now, the order of those 1 through 9 is not necessarily set in stone. As you can see over to the right-hand side, I say the order is flexible, because you cannot optimize all 9 of these within a building. It's simply impossible. There's too many variables at that point. There's always going to be a little give and take on these. Now, you can argue that the first 3 might need to always be the first 3. I mean, performance requirements, you know, if you've got an energy performance target, you have to be able to hit that target. Capacity requirements is, well, the mechanical systems have to be designed to be able to heat the building and cool the building in the worst case scenarios, you know, the coldest day of the year, the hottest day of the year. And spatial requirements. You know, we're trying to do more and more with less square footage. The mechanical system that you specify has to fit within the available space within the building. And sometimes mechanical systems can take up space that could otherwise be used for leasing or rentals or residential and generate profit. But after that, you know, first cost, operating cost, energy use, reliability, flexibility, and maintainability, those orders can definitely shift around. I mean, you may be trying to build a high performance building, and you really don't care about first cost. You just want the best building you can. So that might be down the bottom of the list. At the same time, you may be very sensitive to first costs, and maybe not so sensitive to operating costs. That is, for example, in the condominium development market is very common. You know, the condo developer has to build the building, so they're in for the first costs, but the operating costs are not going to be on the condo developer. That's going to be passed on very quickly to the tenants and the condo corporation. So, you know, in their case, the order is not going to be exactly the same. But understanding your order for your project of these items and what are the limiting factors is really the first start. Because if you try to optimize all of these, you're going to end up in an endless iterative design loop, which you can kind of see over the left-hand side. And ultimately, you're not going to get an answer, or you're going to get a suboptimal answer that kind of tries to optimize everything, but really optimizes nothing in the end. So this is a key place to start when you're thinking about mechanical system design. Now, the other part of that, though, is what is your target? What are we actually trying to get to, right? So let's start with the graphic in the middle, types of green buildings. So let's look at high performance. Everybody talks about net zero buildings, but a net zero building unto itself, if you just tell me that you're trying to build or retrofit a building to be net zero, that's not enough information. Net zero is not a specifically defined term. So you can kind of see a breakdown of how the Pembina Institute here in Canada has broken down what are, you know, called net zero buildings. And it starts with net zero energy ready buildings. These are buildings that are efficient, that may only need solar panels in order to become actual net zero, but they could still use carbon. They could still have carbon emissions from them. So because net zero, you can translate between electricity, equivalent electrical energy, equivalent natural gas energy, and still end up with technically a net zero building. You know, then we get into net zero energy. This is where, okay, you have the net zero energy ready, but now you've added the solar panels or whatever else you needed to add on site to actually get to net zero. But then you get into net zero carbon. So now you're talking about a fully electrified building. There's no gas. You're not making any carbon emissions from the site. But net zero carbon and net zero energy are different. And that's why you have to be more specific. Then you get to zero carbon, where there's literally no emissions, and you're not doing any offsets for emissions through renewable energy credits or anything like that. And then eventually you get to zero carbon plus grid interactive buildings. And grid interactive buildings are going down the path of microgrids, of communicating with other local buildings, with sharing energy with local buildings, not something we're building up to, not something that you can really point to and say that's being done holistically anywhere, but grid interactivity, microgrids, local grids is where the building market is going, so that we can get away from this central power plant paradigm in the future. And you'll see why at the end, but that's essentially. Now, the other possible targets, and actually even more common, is, okay, I'm developing a building, I'm retrofitting a building. Am I going for LEED? Am I going for Energy Star certification? Am I going for ZERG, or zero energy rated home? Passive house is becoming more and more popular standard, and it's actually really the tightest building standard in the world. Then we have, so those are all rating systems. Then we have regulations like the Toronto Green Standard, which I'll talk about a bit, and the BC Step Code. Also, the CMHC, or the Canadian Mortgage Housing Corporation, they have mortgages available for developers, but a lot of those mortgages are tied to energy targets. So, which may not be the same as other energy targets. So there's a bunch going on here. And again, it behooves us to understand set the target early for a development in order to make sure that we're working towards a defined target and we're not trying to over or under exceed, and really understanding what we're trying to get to. Now, if we look at the Toronto Green Standard, specific to energy. Now, there's a lot going on in the Toronto Green Standard that's outside energy. There's construction site waste, there's green roofs, EV car charging, renewable energy. There's all kinds of stuff going on there. But in terms of the pure efficiency aspects, the pure efficiency requirements, it comes down to 3 metrics. TEDI, or thermal energy demand intensity, which is the annual heating delivered to the building for space conditioning. Notice, not cooling, just the heating. TEDI is only heating. Then there's TEUI, which is the sum of all the energy used within that building. So that's heating, that's cooling, that's plug loads, tenant loads, everything going into that building, minus the site renewables. So if you have solar on site, if you have wind on site, which is not very common, but if you have types of solar on site, typically there is some offset there for the TEUI. And then there's also greenhouse gas intensity. So that's the total greenhouse gas emissions associated, again, with all the utility usage on site, primarily driven by natural gas. Our electricity in Ontario is not carbon free, but it's very, very carbon light. Especially compared to some other jurisdictions in Canada, like Nova Scotia is pretty bad. Alberta is the worst in Canada. Quebec is actually the best, because Quebec virtually uses no carbon for their electricity. But anyways, in Ontario, it's primarily driven by gas usage. So if you're over on your greenhouse gas intensity when you do the energy model for a building, you have to start to make the systems more efficient, or just switch away from gas. So all of these values are calculated and reported using normalized floor area. So for example, in TEDI, it's annual kilowatt hours equivalent per meter squared of building. So that's how these targets are scaled over any size of building. And realizing that, the tier performance is marching forward on a set path. This is already locked into the regulations. And essentially by 2030 in Ontario, or sorry, in Toronto, all new buildings will be tier 4, or what's called tier 4 today, which is essentially equivalent to passive house. So this is great, because this means that the city of Toronto has basically got their head around, by 2030, all these new buildings are going to be passive, with passive house, equivalent, which is essentially the tightest building rating system in the world in terms of at least pure energy performance. So it's a great path forward. I really want to see the Toronto Green Standard become the Ontario Green Standard, or even better, the Canadian Green Standard, because it supplants the building codes. And unfortunately, the building codes, that process of improving the building codes and changing the building codes moves very slowly. So these overlay regulations are a way to accelerate our transition to a low energy economy. Now, when we're talking about optimizing a building design, we don't start with the mechanical systems, right? Let's first understand how we lose energy from a building first, before we even start talking about design. So the first way is the building envelope, right? We lose energy from buildings. We lose heating, we lose cooling through the walls, through the windows, through the roof, through the ground, right? And the primary drivers for building envelope losses are insulation values, the window to wall ratio, the effective insulation value from a window, the air tightness of the building envelope, and the thermal bridging. And you can see in the image there below some of the things that go into a high performance building design, like continuous insulation, high performance windows, shading and solar design, getting rid of thermal bridging. But it all starts with that envelope. The mechanical system can be as efficient as superhumanly possible, but if the building envelope is just allowing energy to leak to the outside, we're never going to get the performance out of the building. The next part is the ventilation. So we do need to pressurize the buildings, right? Buildings need to be slightly positively pressurized. The reason for that is we don't want buildings acting as it's sucking in untreated air from the outside. That has two issues. If the building is negatively pressurized because you're exhausting more than you're supplying in terms of air, you're actually driving the case where you're going to get air infiltrating through doors, through window cracks, all those types of things. That air is not only untreated, so it's not heated or cooled, so it could be too warm, too cold, drafts. It's also unfiltered, so you actually bring in outdoor contaminants, or can bring in outdoor contaminants into your building because they're not coming through the air handling systems, which have filters in them, obviously. So we do lose some energy just from building ventilation and exhaust, but there are steps to mitigate that, including air tightness and including exhaust heat recovery. The last thing, and most people don't think about this, is drain water. So the primary drivers here is we are putting, especially in residential buildings, not so much in commercial, but in residential buildings, we put a lot of hot and medium temperature water down to the sewer, both from showers and dishwashing. And there are ways that we can recover that energy before we even think about designing the mechanical systems or the mechanical systems that are to generate the hot water anyways. And again, I'll show you some specific examples of that. I think people appreciate that, building envelope losses, ventilation losses, but a lot of times we do forget about the drain water, but that is something that we have to consider more as we move into the high performance building space. So now that we know how energy leaves, how do we strategize to minimize these energy losses through these three items, right? Before we even get to the mechanical system. So, multiple iterations may be required. Again, there's no perfect answer. If there's an unlimited budget, well, then there's probably a perfect answer, but there's never an unlimited budget. So we have to start with the building envelope, maximizing the performance of that while balancing it with cost and architectural design. Architecture is that weird intersection between kind of, design and art. And obviously, we want buildings to look good too as well. So there are some considerations there, but how the building is aligned to the horizon. What is the R value? Do we have high R value continuous insulation, low U value windows, meaning that, double, triple pane windows, lower window to wall ratios, right? Wall assemblies radiate much less heat than window assemblies. Specified air tightness, minimizing thermal bridging, like from balconies typically, and also doing some shading systems on high performance buildings. These are kind of all the things we can do to maximize the building envelope performance. When we get to ventilation, we want to use the lowest amount of building pressurization and exhaust that we can. We're always going to need to have a little bit of pressurization and a little bit of exhaust, but we want to minimize that. Air tightness of the building envelope goes a long way. But then we also want to maximize the heat recovery systems. We can achieve up to 90% heat recovery. Again, we'll get into some details later about how that's done to make that more efficient. The other thing is the drain water, right? So first of all, we want to lower water usage in our buildings through high performance fixtures. And then we're still going to use some water and some heat for that water. Then we want to implement heat recovery for the drain water. And after we've done all that, then we can start thinking about sizing and even specifying our mechanical systems because we've minimized the load on them. Using this is kind of the process that has to be used. If we just start with picking a mechanical system without working with the architect on the building envelope and looking at the, air, the heat recovery possibilities, both on the air side and on the water side, then we're not doing ourselves any service in terms of building a high performance building. Now, the basics of mechanical systems for buildings. Indoor spaces require heating and cooling. They also require ventilation. Ventilation being both keeping air moving within the space, also bringing in a certain percentage of outdoor air to freshen up the air within the space. So, at a very, very simple level, what happens is that air passes over a coil or a heat exchanger containing either a hot or cold liquid or gas. The picture here, you see it's a chiller and a boiler. So it's cold water from the chiller, hot water from the boiler. But the air passes over that. It could also be combustion gases if we're burning gas directly for heating. It could also be refrigerant if we're talking about a refrigerant-based system. But either way, we're passing that air over that hot or cold liquid or gas. That is changing the temperature of the air. We then supply that air to the ventilated space. And then we also typically have some return air, which is coming back and being mixed with the outdoor air before it's recirculated again. So this is kind of the basics about how we get, how we condition our spaces within our buildings to keep the temperature under control. Now, if we go back in history and look at pre-industrial revolution, how did this all start? Well, we used to heat buildings with campfires, fireplaces, and wood stoves. There also used to be ancient kind of solar type of heating systems that were used, where they would use rocks or other medium to capture the heat of the sun during the day, and it would slowly release at night. For cooling, pre-industrial, we had windows, we had natural stack venting. We also did evaporative cooling. It was thousands of years ago that, humans figured out if you hang a wet mat in the doorway of your house and then a breeze blows over that wet mat, it will produce evaporative cooling and actually cool the interior of your little hut a little bit. This is known, and I think we see examples of that when we go into near a river. We can feel that kind of evaporative cooling even on a warm day or near a lake. So those were some of the ways, the primary ways that this was done before we really had true mechanical systems. Obviously, in these kind of cases, the control was not precise. The systems were generally not centralized. It was the best we could do at the time. Now, after that, really the original centralized heating solution was steam. So, steam would be generated by heating a boiler with water. One of the things that makes steam really easy, and why it was one of the first centrally adopted systems, was you don't need any pumps. Steam naturally flows into a piping system because it's pressurized. It's literally a pressurized vapor. So you don't need pumps to distribute it. So the steam then flows into the individual loads, like the radiator that you see. And then that's the heating side of the system. Then there's the condensate side of the system, where after the steam passes through the loads, whether it's a heating coil, heating radiator, the steam actually turns back into water. So it gives up all that heat. And then it's pumped back. The hot water is then pumped back into the boiler system to be reheated. You're still going to see these in old buildings and district energy systems, but not designed into new buildings. Probably hasn't been designed into new buildings in decades. And, these systems are being replaced as well because they're very inefficient, poor control, heavy maintenance. There's really no reason to be using these anymore. So they are on their way out of existing buildings and have not been put in new buildings for many, many, many years. So if we start to look at modern HVAC systems, right, I'm going to break it down real quickly here. So we have what I call direct heating and cooling, which is where we're using electrical energy or natural gas to directly heat or cool the space. We have also air sourced systems and ground sourced systems as well, which is kind of where the future of heating and cooling is going. So starting with electrical, I think electrical heating is pretty straightforward here, right? We all know about electric baseboards, little electric spot heaters, right? So baseboards and plugins. Straight up electrical heating can be used actually in larger equipment. There are in the Northern Ontario where gas is not readily available, natural gas through pipes. there are electric air handling units. They're very costly to operate, but sometimes they have no choice. There's also delivered propane alternatives, but sometimes even those are not accessible for some of these remote locations. So these electric heating is very simple, but is expensive to operate. The other way we use electricity conventionally for direct heating and cooling is with compressor-based systems with refrigerant-based cooling. And we know these as obviously home air conditioners, like you can see in the bottom left-hand side. These are called DX or direct expansion systems. That same type of system is essentially what's in a rooftop air handling unit as well. Most of those use direct expansion systems. They just look a little different, but exactly the same type of operation. We also have chillers. So chillers are compressor-based systems, but they generate cold water with the refrigerant charge, and then the cold water is distributed to the building. So these are really the most common forms of cooling that are directly electrically generated. Chillers are actually the most efficient way to deliver cooling to buildings. There is nothing that beats a high-performance chiller for cooling efficiency compared to anything else. But they're not, again, always the most applicable, especially in our climate here, where our loads on a building typically swing much more towards heating than cooling. I know that may not seem like that on a day like today when it's pretty hot outside, but overall, we use much, much more energy as a total to heat our buildings in the winter in Canada than we do to cool them in the summer. Now that's changing. Obviously, we know climate's changing. Over the next 20, 30 years, it looks like our climate in Toronto area is going to move from basically Washington, D.C.'s climate is going to move up to Toronto. We're going to shift a whole climate zone due to climate change. That's going to change that equation on cooling a little bit. But I still suspect we're still going to be pretty heating dominated in Canada for the next century or more. Now, when we look at gas, how do we use gas with combustion to heat buildings? Well, we use furnaces. That's typically like in your house. We use rooftop units, like you can see. You can even see the yellow gas line there for that rooftop unit. We also use radiant tube heaters. Those are more indoor style heaters where we're just trying to blast heat into a space, especially warehouses, and unit heaters as well. Also typically used in more larger buildings, loading dock areas, more rougher, unfinished areas where we use unit heaters. This is obviously extremely common way to heat these days. Typically up to 80% efficient. However, some of these types of equipment can approach 90% plus efficiency, but the typical base efficiency when we're combusting gas is 80% maximum. But we're expecting a lot less of this equipment in the future due to carbon taxes and emission reductions. We're going to have to get out of this paradigm of combusting gas directly. And that's kind of where you're going to see the next systems kind of going. So and the other way we combust natural gas is we use it in boilers. So this is more common for larger buildings. It's also essentially what you do in your hot water tank too at home, where we burn gas to heat water. We can do it in a water tube style boiler or a fire tube style boiler. They essentially have the same type of output. Again, very common. Modern condensing unit boilers are actually up to 96% efficient. But again, we expect less of this type of equipment in the future due to the fact that we have to stop combusting gas and using the gas combustion energy directly. Otherwise, we're never going to hit our carbon reduction targets, emission reduction targets. We're just not going to be able to do it. So then we move into the air sourced world. So this is heating the air with outdoor air energy. So the traditional systems that are most commonly deployed are compressor based again. So they use electricity with refrigerant charge. There's different system styles. We can have split head systems, which is kind of like what you see at the top, where you have one head inside, one head outside. It's a very simple example. We can have air to air systems, air to water systems, and also variant refrigerant flow systems. That kind of looks like the picture in the bottom right-hand corner. That's a variant refrigerant flow system where there's one outside unit and multiple heads connected to the refrigerant lines in order to distribute that heating throughout the building. Those systems also do cooling as well. Now, this way of heating and cooling is becoming much more popular. It's much more efficient than obviously straight up electrical resistance heating. In fact, the efficiency of these types of systems can be 3 times higher. And the reason is the efficiency is there. And sometimes it's a little hard to see, but is because we're actually pulling heat out of the outdoor air. And that's why there's no free lunch, right? The rules of thermodynamics, the laws of thermodynamics still apply anywhere. So we're putting electricity into these systems, but the efficiency gain is coming from the fact that we're actually extracting heat from the outdoor air. And these systems can work down to as low as minus 20 degrees Celsius. I know how strange that must sound, because minus 20 degrees, you're not thinking there's a lot of heat in that outdoor air, but there is still extractable heat in that air that we can use to heat the building. It's not terribly efficient at minus 20, don't get me wrong, but it's still more efficient than just using the electricity directly. However, once we get below minus 20, physics basically, the laws of physics stop these systems from kind of working anymore, where we can't really extract any heat out of the air. So we typically need some kind of backup heating system, even just a small one for those adverse events, because we can still get down to minus 20, minus 25 even in southern Ontario. Now, another different style of air source system, but we're starting to see more of these, is a gas absorption based system. This is a technology that Enbridge is actually promoting right now. Again, we're extracting heat from the outdoor air, but instead of putting electricity into these units, we're putting in natural gas. And it's running through an absorption refrigeration cycle rather than a compressor-based refrigeration cycle. But the underlying principles are still the same. So this takes, if you look at these as a replacement for a typical boiler, which is, can get up to 96% efficient these days, these gas absorption heat pumps can get up to 164% efficient, typically operating probably more around 130%, but we're still gaining somewhere between 30, 40, maybe up to 50% efficiency versus a conventional boiler, because we're using that outdoor air again as a heat extraction source. So this is emerging, but it's emerging in the sense that Enbridge is currently piloting this. And they see this as a transition pathway between, conventional gas fired equipment like furnaces, like boilers, and going to fully electric buildings. So this is a way to transition our energy systems while still using gas at a lower cost. And still keeping our operating costs a little bit lower until we can truly transition to, like, say, a zero carbon economy. Now, the last type is ground source systems. So ground source systems is where we're heating with ground energy. So similar to air, we're extracting heat out of the ground, and we're actually rejecting heat into the ground in the summer in cooling mode. So the cycles reverse summer versus winter. You can see that in the graphic at the top. So again, these are refrigerant-based systems that you put electricity into, and then they have these loops of water in the ground. Now, the loops can be vertical. Vertical wells are typically very deep, somewhere between 400 to 600 feet each. Depending on ground conditions. And then we can also have horizontal wells where we do shallow wells, maybe 10, 15 feet, but we lay them out over a larger area, much more typically appropriate for schools who have large yards or rural properties. When we're talking in the city, we pretty much have no choice but to do vertical wells because we don't have the ground space to do that. So you definitely get increased efficiency compared to any kind of air source system. There's no need in these types of systems for a backup heating source. Unlike the air, once it gets below minus 20, we can't get any heat out of it anymore. The ground never gets like that. So we can always use these any temperature outside. Certainly there's a higher initial cost in air source systems because we need to drill these wells and put the piping in. There's a cost to that, and certainly that drives it. But the first cost is going to be offset over the next few years by the operating cost, the lower operating costs. So it's a trade-off of upfront capital versus ongoing costs. Really, this is the premier choice for buildings in Canada, if the site conditions allow for it. And I guess if your budget allows for it too. But let's just assume we're trying to do the right thing here. If the site conditions allow for it, if we have enough room on the site, we have the place to drill the wells, the soil conditions and the rock conditions underneath are acceptable, which they are in a large part of Canada, then this is really the premier choice. And when we look at that, more specifically, like this is the idealized type of system for buildings in Canada, especially larger buildings, is heating with the ground energy. So you can see a diagram of what one possible ground source system can look like. So the system, first of all, is sized for 100% of the building loads. It's centralized. It uses centralized heat pumps in the mechanical room, and then it distributes hot and cold water to the building to take up the heating and cooling load. This type of system is zero carbon operation. Again, there's no backup system required. The system efficiencies and the maintenance is primarily contained in the mechanical room, which again hits one of those key design criteria of ensuring that the efficiencies in the system can be maintained without having to go everywhere in the building. And this type of system, it's easy to plug in alternative energy sources, such as solar, such as district energy, because what you're actually distributing to the building is just water, hot water, cold water. So all those connections to other energy sources as we transition, if you need to transition, if other options become available, are now just all done in this mechanical room. So this is really, really the premier choice. Anything other than this is kind of a downgrade at this point in time. Understanding that, yes, not everybody has the budget to do this, and not everybody has the site conditions to allow the ground loop field to go in. And if the ground loop field can't go in, then obviously this is not achievable. Now, heat recovery. I talked about this a little bit in the beginning as kind of one of those key things before you even get to choosing, or at least sizing the mechanical systems. So, ventilating buildings does always require some air to be exhausted from the building. There's just no choice. For example, bathrooms by code have to have some kind of constant exhaust out of them, right? Whether it's in your house, that's probably more tied to a switch, but in bigger, larger buildings, commercial buildings, multi-residential buildings, there's always got to be exhaust from the bathrooms. So that air has energy that we're exhausting. The trick is we need to recover that in high performance buildings. Traditionally, that energy was not recovered. We would just vent that bathroom exhaust outside because the exhaust itself needs to be vented. We can't recirculate bathroom exhaust air into the building. That just would not be good for health, for smell, for anything. But there are ways without actually mixing the air that we can recover the air through heat exchangers, through heat cores, through heat wheels. So you can see at the top images, that's an example of a typical ERV, or energy recovery ventilator system, that is put into all new homes that are built now, all new single family homes, as well as most new tall multi-residential buildings. Those are put in suite to create that constant exhaust, constant ventilation with fresh air while recovering the heat from the exhausted air and the cooling as well. And then the image on the bottom is more of a centralized unit for a building. So this is a bigger air handler that's essentially doing the same thing, but it's on the roof and it's capturing, it's ducted into the suites, into the spaces to exhaust the air, to bring in the fresh air, and to capture the heat from the exhausted air, and effectively return it to the building up to 90%. Those are some of that style of unit is actually some of the most effective heat recovery that you can do on a building. But as I mentioned also too, we have to think about the heat recovery from the water side. And this is something that is, again, not on a lot of people's radar, but is a critical component going forward. So because this drain water contains more energy than most people typically realize. So primarily we're looking at this in residential buildings. Most commercial buildings don't have a lot of hot water usage. So it comes down to the showers and the dishwashing. So there's really two primary ways that this can be done. The first one is what's called passive recovery using power pipes. So that's the image at the top, where essentially a copper tube wrap is put around the drain pipe so that the incoming cold water is preheated as it runs to the shower by the drain water that's coming out of the shower. So the water never touches each other, but you're capturing some of that hot water energy that's going down. That can actually recover somewhere between around 40–45% of the energy that we're losing out of that hot drain water going out to the sewer. But if we need to get super advanced, if we need to have just a really, really high performing building, we can do active recovery with a heat pump style unit, which is what's shown in the bottom picture there. Now, the trick is with these, it's just a regular heat pump, which is using electricity to extract the heat out of this hot drain water. The real key, and what only 1 or 2 vendors in the world have been able to figure out, is how to effectively do that, because you have to separate the solids, right? Drain water is not just liquid. There's also some solid components in there as well. So there's at least one company and maybe one other that has figured out a way to automatically separate the solids, create a really maintainable system, and those type of active heat pump based systems are really, really effective at extracting most of the heat out of the drain water and returning that to the building. So that's where the market is going for super high performance. Now, talking about a few other things really quickly, water efficiency, I touched on that. Remember, water is a more expensive utility than most people realize. In fact, there are a lot of older residential buildings in Toronto where the cost per water per suite annually is more than the cost of the natural gas or electricity. So it's a big cost for landlords or anybody who owns a home. You also got to factor in the heating energy too, right? We bring in water, we pay for that, but we also pay to heat a fraction of that water. So ultra low flow fixtures is really where the market's going. We're talking about toilets that are down to 3 liter to flush residential, 3.8 liter commercial, and lavatory and kitchen and shower faucets that are very, very minimal flows. But we've come a long way. These modern low flow fixtures offer really good performance with these reduced flows through creative use of aeration. So you can get down to these levels, and people, honestly, most cases won't even notice they're using ultra low flow fixtures, but the performance benefits will be there. Also, appliances. Energy Star is the #1 rating for appliances. So every new appliance comes with an energy efficiency, sticker, tells you how much it's going to use, but only if it's to a certain level of efficiency will it get the Energy Star rating, meaning it's in the higher end of efficiency. That includes dryers too as well. Today we have ventless dryers, they're called heat pump dryers. So by eliminating the vent, you actually eliminate an air penetration point into the building. You also, potentially eliminate lint buildup and a fire trap point too as well. Just one thing to keep in mind when you're searching for appliances is that not all Energy Star appliances are equal within a category. So you have stoves, you have fridges, you have freezers. Their energy performance and Energy Star is over a range. So I put a link in there. I suggest you contrast and compare different appliances, using the Energy Star database to figure out the one that you're thinking of buying. Where does that really fall in terms of all of the Energy Star appliances in that category? Because it could be very, very efficient, or it could be, one of the least efficient unit that still qualifies for the sticker. Now, real quickly on-site generation, the other thing we can do, with our mechanical systems is try to capture as much energy as we can on site. And that quote, that first bullet point there, all the sunlight that hits your property and building is yours to use or waste, that's me. I kind of came up with that a few years ago because that's kind of the way I think, right? Is that, the sun that hits your property, you can do something with it or you can just let it fritter away. Now let's assume for a second that grass, trees, shrubs, anything that's growing, biologic, that's a useful use of sunlight. But sunlight that's hitting your roof, sunlight that's hitting your parking lot, sunlight that's hitting the sides of your buildings, the opaque sides of the buildings where there's not windows. I think all that's a waste unless you're collecting that energy, right? So when we talk about solar, everybody's minds usually first goes to solar photovoltaic or solar electric, right? So the primary locations for those are usually the roofs and the parking lots. The parking lot carports, like you can see in the bottom picture, are starting to become more popular these days, and they're fairly cost effective. And they offer some additional advantages, like they're a snow shelter for your car, they're a rain shelter for the cars in the parking lot. There are entire shopping malls in the US now that their entire flat parking lot, which are typically just acres and acres, are completely covered with these solar panel carports. So, we're starting to see transition this way. Secondary, you can put solar PV on the side of a building, but it's not as efficient or cost effective because you don't get the right angle to the sun. But there's other alternatives to solar PV. We can also make solar hot water. Solar thermal systems are something you can even just create in your garage. There's no electronics in them. We're just capturing the sunlight to heat water. So you can even do homebrew systems like these. Primarily, we see these on roofs and sides of buildings. They capture sunlight much more effectively than solar photovoltaic. So the efficiency on a solar PV cell is only about 20%, maybe max 25%. For the best in class panels, that meaning that 75%, at least 75% of the sunlight hitting your solar electric panel, solar PV panel is wasted. It's not captured. Whereas solar thermal can be up to 90%. It's not nearly as common, these setups, as PV, even though they're technically much simpler. There's multiple reasons for that. There's certainly a knowledge gap in the market. There's reliability and maintainability issues, especially if the system's not designed well from the beginning. The return on the return on investment of these, the simple payback period, can be 8, 10, 12 years. But that's kind of similar to solar electric too as well. But the payback on these types of systems, whether it's solar electric, solar PV, or even the next one I'm going to show you, get better, obviously, as utility price increase over time. So that last part is solar air or solar air preheating, where this is called a solar wall. So the sunlight hits that black wall that you see, where this is an air handling unit in a room on a roof of a building. All that black wall around it is a solar air preheater. So as you can see in the image at the bottom, the sunlight hits the black wall. It actually heats the air in behind the wall, and that air is then sucked in to the air handling unit for basically preheating the air. So this directly offsets the heating energy that the unit needs to use to achieve its final discharge set point. Uncommon, but there are examples of these, but I would say they're fairly uncommon. It was actually invented in Canada, this technology. Bestly suited for buildings that are flat sides or mostly windowless. Really simple technology. There's no moving parts with this. It's just a cladding system. And the wall is almost always inactive or bypassed in the summer months. In the summer months, all that air we're preheating, we typically don't have anything to do with. But as a total energy balance for a building, if we're looking at the solar radiation, we really do have to consider what's the mix that's going to be correct, or the right mix for us for PV, thermal, and solar air preheating. There's always going to be an optimal answer between those three. Last is also on-site generation with natural gas. This is combined heat and power. So one of the fundamental problems is when we burn fossil fuels, primarily gas these days, could also be oil too as well, but primarily natural gas. When we burn that at a centralized power plant, we generate electricity, but we also generate heat, and that heat is typically just pushed out to the environment at the central power plants because there's nothing to do with the heat. When we burn natural gas on site in our own essentially generation system at our building, we can capture not only the electricity, but we can capture the heat as well to preheat domestic hot water, to heat hot water to heat the building with. So we can take a typical efficiency of 30 to 40% at a power plant if we're burning the gas, and that's net efficiency all the way from the fuel combustion, from the fuel entering combustion through the distribution to the building. Or we can get up to 75 to 90% efficient if we use it. If we use a combined heat and power system where the electricity and the heat are being both used directly at the building. This was popular in Ontario for a lot of years due to low gas costs and generous incentive programs in the last Save on Energy framework, but the installations have started to slow down. The incentives have gone away, and likely due to the carbon tax, we're not going to see much more of this in the future because it's going to get too expensive to just combust gas. And alternatively, district energy. This is not going to be applicable everywhere, but we do have district energy systems already. We have one in Toronto that's run by Enwave. We have one, the Windsor, Ontario also has a small one too as well. Ottawa, Ontario, the government has one for a lot of the buildings. So this is where we're producing heating and cooling centrally, and then it's distributed by piping to nearby buildings. Originally, these systems going back a long way were steam. The newer systems are hot water, chilled water. They have several benefits. Higher efficiency because you can get higher efficiency out of larger centralized mechanical systems that are all in one locations. The buildings become really simple because they just have heat exchangers to take the heating and cooling energy from the loop to the building. So that lowers capital and maintenance costs for them. And you get greater redundancy and reliability overall because you have multiple sources of generation, multiple buildings connected together. But this type of system is typically only useful or only cost effective in densely populated areas, does require a lot of underground infrastructure. So it's not something you roll out quickly. Although we are starting to see more developments, like if a developer is planning on putting 5 towers on a single site, they might choose to do one heating and cooling plant for the 5 towers that they're building, rather than in the past, they typically would have put a boiler, chiller, or a separate mechanical system in each of the 5 buildings. So we are starting to see more use towards this. And certainly, if you ever go to Europe and you have a chance to look over there, they have a lot more district energy systems that are much more deeply integrated. For example, Copenhagen, Denmark, about 80% of all the buildings, residential, commercial, and industrial in Copenhagen, are serviced by district energy systems. So they have a much deeper penetration over there, and I expect to see more of that in North America over the next several decades. So finishing off this section, net zero buildings, you know, when we're evaluating, this is a real example of something we did here at NERVA for evaluating choices for a mid-rise MERB. So this developer wanted a net zero multi-unit residential building located here in Ontario. So we did up a quick evaluation matrix for 4 common mechanical systems that they could have chosen. Now, 1 is the best, 4 is the worst score, so you want the lowest score possible. And as you can see here, the really conventional type of system, the chiller boiler type of system, won out in terms of total score. But the fundamental problem is, though, that system really cannot be made net zero. The efficiencies are not there, even though that's the type of system we've used traditionally for years. So the next one up was the ground source system, the geo pump, and I'll get into some more details on that in the next slide. That had the next lowest score, but it actually can be net zero. The other 2 options had higher scores because they had higher costs, higher operating costs, higher life cycle costs. Certainly the last option there, the VRF Geo, can be net zero, but it comes at a really high cost, and it's just not going to be good. So this idealized net zero system for a pathway for multi-unit residential buildings, but certainly can be applied with a little bit of modification through a wider class of building stock. Are, you know, 100% centralized ground source heat pump system, you know, with a lot of heat recovery, 90% efficiency heat recovery, very small ventilation rates, 7 to 15 CFM per door. We got to do the drain water heat recovery. We got to do the solar PV panels. We probably want to mix in solar wall or some solar thermal, capture some additional solar energy to reduce our load. And, you know, put all together with a great walls, window and roof, the whole building and inner suite air tightness, and some smart controls. This is kind of a basic roadmap about how we're going to build net zero buildings, tall net zero buildings in Toronto and anywhere in Canada, to be perfectly honest. You know, there's always going to be bits and pieces that you can pull in, pull out, adjust here, adjust there. But this is one of the easiest and probably most cost-effective and future-forward paths to get there. So really quickly, because I only have a couple minutes left, I do have some slides in here just talking about COVID-19 and the relationship to ventilation systems. I'm not going to get a chance to go through them all, but certainly the current pandemic has forced building owners and operators to implement strategies to decrease the risk of aerosolized virus transmission within their buildings. You know, if we look at that, this is an example from China very early in the COVID pandemic, where they were actually able to trace this transmission of COVID within this restaurant where the air conditioning unit on one side of the restaurant was turning around air, and an infected person got a whole bunch of other people infected that night. Yet the people on the other side of the line, the other side of the room, didn't get infected at all, just because due to the air movement. So it goes to show you just how aerosolized COVID is and these micro droplets and how risk of transmission can be. And if you remember, this was long before the Delta variant, which is even a higher rate of aerosolized transmission. So this is a really important subject. I think indoor air quality due to COVID-19 is always going to be something we're going to be talking about in the future, but at a very high level. You know, we need to improve filtration in buildings, keep fans running during occupied times, keep, you know, disable demand control ventilation, keep a lot of outdoor air coming in the buildings, flush buildings pre and post occupied times, certainly sealing our ductwork. There are some really high-tech air purification systems, ionic-based air purification systems, and controlling our humidity are all things that building owners are doing today. So, whatever you do, and I know you guys are looking for, a secret clue. Well, you got to keep your motor running, because you got to keep your air moving within your buildings in order to keep the air quality high, in order to prevent the risk of COVID transmission. So thank you for this opportunity today. Looks like I'm right on time, even though I had to skip by some certain parts. Certainly look me up on LinkedIn. There's my name, there's my link. I hope you appreciate those memes I put on there to close this out. Those are some of the most funniest HVAC related ones that I could find when I was putting this together. So thank you everybody for your time, and I'll see you in the Q&A session.